get this going. Here we go. Thank you very much. James just gave a beautiful overview of jets, and I get to talk about the very best kind, and that is the jets from gamma ray bursts. And how I would like to talk about how ngVLA and SKA are really the key for us to finally understand the physics of these. So what I'd like to do is remind you a little bit about what gamma ray bursts are and how the radio observations have really upended our standard view of what's going on in these massive stellar deaths and their remnants. So I'll talk about both that in a macro physics population sense and individually with the plasma physics. I'd like to tell you about some new theoretical and computational approaches that we're implementing to help uncover where we need to focus, where the mysteries lie, and then ultimately how radio follow-up can help us solve these mysteries. Okay, so as a reminder, I won't repeat too much of what James already said, but a gamma ray burst is a burst of gamma rays that lasts, from less than a second to tens, hundreds of seconds, followed by long-lived afterglow across the electromagnetic spectrum from hours, days, months, weeks, years, and we get about 10 to the 52 ergs of energy out in these events. In a very short time, most of the energy is in the gamma rays. The gamma ray burst part is sort of grouped into two groups, those that last less than about 2 seconds and those that last more than 2 seconds. And we think the short ones are associated with the merger of compact objects, double neutron stars. The longer ones are associated with the deaths of massive stars. This is not a perfect grouping. There's been lots of challenges to this recently. That's very exciting. But more or less, this holds up well with the data and the theory. So either way, in both cases, you're left with this central engine. I like the black hole accretion disk model, but you can have a neutron star as your central engine that launches a relativistic, highly relativistic jet. Internal dissipation processes like shocks or reconnection produce this highly variable seconds to tens of second gamma ray burst. And then as the jet front sweeps up the external medium, it decelerates and emits across the entire electromagnetic spectrum. That is our afterglow. And the emission mechanisms, especially for the afterglow, are really well fit by synchrotron, and we have sort of a nice overall picture of how this works. But the radio emission has really challenged us lately. So you don't need to read all of this text, but this is just a sampling of some papers only over the last few years where radio, I've underlined where the radio emission they're saying has upended what we think. And one of them I'd like to point out is by Genevieve Schroeder, who is here at this conference. Her poster is right there. Very interesting work done on the radio afterglow, and I encourage you to look at her poster to learn more. So I'm gonna focus on two areas where we're challenged in the radio. And the first is what I'm calling macro physics challenges. And what I mean by that is in a population sense, those GRBs with radio afterglows appear to be significantly different than those without. And in the sense that those that are radio bright have a longer gamma ray burst. That internal emission, those internal dissipation processes appears to last longer in those that have radio afterglows, and they're more energetic. The redshift distributions between the radio quiet and the radio loud are not different. In a microphysics sense, I'm sure you all have heard of the boat, the brightest of all time, GRB 221009A. This is a beautiful paper from Laskar et al., 2023. They showed that the radio and millimeter data require the presence of an additional emission component. The temporal evolution is not consistent with synchrotron radiation from a single power law distribution of electrons. Basically, our standard assumptions are violated. Okay, so the radio is weird, and what I'd like to do is talk about how we're approaching the macrophysics and the microphysics problems. Okay, before I do that, let me just remind you, this has been brought up before, but I just want to remind you how extraordinarily multi-scale GRB modeling is. The plasma physics involves length scales on the order of a centimeter or so. The central engine is Schwarzschild length scales, 10 to the 6 centimeters or so. Our hydro length scales are 10 to the 15 centimeters. If we want to understand their evolution throughout cosmic time, we're talking cosmological length scales. So we're, about 30 orders of magnitude in length and time. If anyone does computation in here, that that that's not easy to do with, certainly not with a single code. So we have an approach. I want to highlight my colleague Roseanne Chang here at Los Alamos, who's leading an effort for code and scale bridging approaches to this type of modeling. It's very general, goes beyond GRBs, but I'll tell you in the context of GRBs, we're modeling the progenitor with a stellar evolution hydrocode MESA. Probably many of you are familiar with this. We model different progenitors, which I'll talk about in a moment, and we take that output from MESA, that final state, and feed it into our initial conditions for GR-MHD codes. We use Athena++. There are many others available. I will tell you a little bit about some modeling that we do with particle and cell codes of the relativistic jet. This is a really hard problem, but we have some exciting approaches there as well. And finally, what I'm really excited about is understanding what these mean and how these fit into our global picture of our universe, of stellar evolution in our universe, and we're doing some population synthesis in that regard. So one of the things that we're testing is this radio bright, radio dark dichotomy, and we've conjectured that the radio bright GRBs are a result of a massive star collapsing in an interacting binary system, in particular with a closely orbiting compact object companion. Whereas the radio dark, we think might be the collapse of a single massive star. And here I'm talking about long GRBs only, those that last, the gamma ray burst lasts about tens of seconds. So why? In an interacting binary system, this massive star has the potential to have more angular momentum. It can be spun up, and it can also have a more extended circumbinary circumburst density profile. So what? Well, more angular momentum allows you a more massive disk, a potentially lower accretion rate, and this allows you a longer jet, a longer lived jet, longer duration for those internal dissipation processes. So that would explain the longer gamma ray emission. But in addition, the extended density profile is going to give you brighter radio emission. So both of these things, this massive star collapsing in an interacting binary can accommodate what we're seeing in this radio bright population. And so there was a paper just last year kind of doing order of magnitude estimates of that, but now we're simulating this and testing it. And here's some output from 2 MESA simulations, and I just want you to focus on that middle panel there. It's the angular momentum, and in particular on the circles. That's the evolution of the angular momentum of the massive star throughout its lifetime when it has a black hole companion that's orbiting at a 3-day orbital period. And we can see that the star gets spun up, and we're getting the angular momentum we need to launch this relativistic jet to create a larger disk, a longer lived disk. We've begun to put some of the MESA simulations that work. We're getting information of, okay, which initial conditions allow us, what kind of progenitors allow us the possibility to make a GRB, and we're putting those into this population synthesis code COSMIC. Here I show a histogram of orbital periods of binary systems in the bulge, a thick disk and thin disk components of a Milky Way-like galaxy. And please take my numbers with a grain of salt, but the main takeaway from this is that we're finding enough of these to be consistent with rates of GRBs. So we feel excited about these as a possibility. Like, not only can we make one work, but we think they might be okay with populations as well. So, however, at this point in GRB astronomy, electromagnetic emission is how we learn about them most. And so we need to really understand that plasma physics of the jet. Sorry, this is, my shirt is not conducive to a microphone, but I'll do my best. Okay, so synchrotron radiation is evident in GRB spectra. And I want to emphasize not only in the afterglow, but the prompt emission as well. There's been a lot of papers challenging that, but in fact, it fits the prompt emission, the gamma ray emissions spectrum very, very well. So we know, that means we know there are magnetic fields and energetic populations of electrons in these relativistic jets. Okay, so how do we make those? What do we do? Where do they come from? There was a question earlier about the baryonic versus leptonic and the amount of magnetization. All of this matters. And how do we, thank you. The plasma physics of this is difficult to simulate in the sense of it's a very expensive simulation. And you have to take very tiny time steps. And so we have not yet, nobody yet has simulated these relativistic plasmas to timescales that we need to answer these questions. So I want to tell you about an approach that we're developing, and this is with my colleagues Guanjie Chen, Chen-Kun Huang, and Fan Guo at Los Alamos. And what we're doing is we're as long as you're not in a vacuum, you can transform to a reference frame in any plasma simulation where an analytic solution exists. That frame is where the electric and magnetic field are parallel. So we do that, and then we solve the equations of motions exactly analytically, and then we transform back to our lab frame. And what this does is allows us to take a much larger time step than what PIC simulations normally limit you to. This plot here is just showing relative energy error in the blue, and the green is what you want to focus on relative to explicit particle pushers. We're testing, so it works best for uniform fields. We're testing on orbits, on fields now with just linear gradients, and I'll move on just in terms of time. Things are looking good. Eventually we want to get to magnetic field structures that we see emerging in these PIC simulations where there's more gradients. All of this, so the modeling is super fun, but it means nothing if we can't make it make sense with what we observe. So the solution really lies in the observations by ngVLA and SKA. And in terms of the macrophysics populations and solutions, this is showing predicted light curves. The blue is from a star collapsing in a binary system, and the green is from a single star in the radio at different bands, 1.5 gigahertz, 3 and 6 gigahertz. And the band shows roughly, it's very rough, I just drew a straight line, it's not perfect, but the sensitivity of ngVLA and SKA. So we'll be able to distinguish between these models and test this. From a microphysics point of view, so James showed this. This is actually a plot that I made. Alessandra and I put that together for a white paper. And I want you to focus on the red here. This is the reverse shock at 8.46 gigahertz. It shows up early and it's bright. And the boat, back to the boat GRB, indeed, these early time observations of the reverse shock in the radio allowed us to break all the degeneracies. Modeling GRBs is hard. There's a lot of parameters involved. The early time reverse shock observations are key. And in this case, it allowed us to constrain the size to 5.6 times 10 to the 16 centimeters, the Lorentz factor, the internal jet energy. The early time radio is crucial to helping us really get a handle on that internal microphysics of GRB jets. So let me just summarize here. Again, it's the radio that helped us learn that we don't really understand GRBs from both a progenitor and a plasma physics standpoint. I'm really excited about a number of computational approaches that we're employing, and others as well, to help uncover where these mysteries lie. And radio follow-up with the ngVLA and SK is really the key to solving these mysteries. And I'm really excited about what's to come. And I'll end there. Thank you.
Hey, questions over there.
Hi, Nicole. Thanks for the great talk. I was wondering, is theory able to predict the angle of the jet relative to the plane of the binary? Because you might be able to, if there's variation in that, you might be able to get lots of variation in density.
That's that's an amazing question. I mean, all I can say there, we know the jet is going to be oriented along the spin axis of the black hole that comes from the star. I assume that's all going to be in the plane and orthogonal, but that's my simplistic, But that's a great question. Do you have a thought, Tom? Oh, okay. Yeah, that's excellent. Okay.
Were you gonna add something? Okay.
Nice talk, thank you.
Thank you.
So I wanted to actually ask partially what Dylan asked and also extend that since in GRBs you talked about radio dark versus radio loud, synchrotron emission is also coming in optical and X-ray bands. Do you see some kind of difference or some kind of binarity signatures in higher frequencies also?
Thank you for that question. I appreciate it. Not significantly, no, not yet. So that's why I feel like the radio is so weird. The X-ray and the optical afterglow between the radio dark and radio loud do not appear significantly different. As we know, GRBs vary a lot, so it's hard in that way, but we haven't seen anything. But we do have efforts to explore other possibilities like their variability properties and things like that. But that is an excellent question. Thank you. And the answer is sadly not yet. Yeah. One thing if I can say on that note, one other dichotomy between these two is we do see that very high emission, the GeV and TeV emission, only coming from the radio bright sources. So that's something.
Okay, Tom and then Joe at the back.
Yeah, so on this binarity issue, would you be able to, if you had, you could have a binary where you had the GRB happen as the first explosion or as the second one?
That's correct.
Would the case where the explosion, where it was associated with the second explosion in a binary look more like the single star case or more like the binaries where it was the first explosion?
So I think that, so it's the second one, it will look like a single star case. Both will kind of look like the single star case, but it's the second one where the interaction we think really matters in the sense of at least the angular momentum spin up and things like that. But you're absolutely right, both massive stars, we have in our cases a black hole companion to our massive star that's making the GRB. That could have also made a GRB. We're focusing only on the second explosion and how that influences it. But this is a great question. Something we could certainly do is see other two main sequence stars and that interaction on the first GRB. That's something to do. Yeah, that's excellent. Thank you.
Hi, Nicole. That was a great talk.
I'm
just interested, kind of following on Tom's question with the binary models there. As you know, most massive stars occur in binaries, and it's not hard to make them interact.
Yes.
The thing is to make sure the star is still rotating rapidly when it dies.
Yes.
And metallicity is obviously the big deal here. So I was just wondering, in terms of your simulations, what kind of metallicity do you assume? And
excellent question. Excellent. And I hope the student that I'm working with will have those results public soon. But we've explored metallicities from the Z, where Z is the fraction of elements above helium, from 0.0001, 10 to the minus 4 to 0.1. So this huge range of metallicities, well above solar to way below, POP3 kind of metallicities. We do see the interaction in all cases, but higher metallicity stars, because they're more puffed up, we get a little bit more of it, and that is something that's coming out. But we are looking at that, and that's a really good point. Yeah.
Okay, any more questions? Okay, there in front.
So when you go to very low flux density with the new instruments and you try to explore like these radio quiet events, do you expect to be contaminated by diffuse emission or possibly nuclear activity in the host galaxy?
Possibly, yeah. And I don't know to what extent, honestly, not being an observer and not knowing the radio emission from galaxies very well. Sure, I think we always have to worry about that. The GRBs are so bright, across the spectrum that, when they're there, they're really there. But it's of course something that we have to worry about. somebody else in this audience is certainly more well-equipped than I am to answer to what extent and that background noise. Thank you. Thank you.
Okay, I think it's time to move on. Thanks,
Thank you so
Nicole,
much.
again.
Thank you.